And what's significant about what happened if that permafrost was to melt?
All the roots in there that have decomposed because they were frozen for so long will start decomposing and releasing CO2.
Okay, so the roots begin to decompose, and it's not the roots' fault that they're releasing CO2, it's the decomposers that are undergoing respiration, releasing CO2 into the atmosphere. In addition to decomposition leading to increased flux in carbon dioxide, there are also a number of microorganisms that are all frozen in place. They've been waiting an awful long time to thaw out and get going again. And a lot of these are methane-producing bacteria and archaea. And what they'll do is, as they thaw out, they'll basically begin to convert soil carbon into methane that ends up going into the atmosphere. So there was a sort of a fleeting statement about a carbon bomb sitting up in the permafrost soils, which is a fairly controversial idea. I think it's the word that's sort of the controversial part of it. But it's certainly true that there is a lot of carbon in those permafrost soils that is stuck in the permafrost soils because it's frozen. And any thawing that's taking place within those soils is going to lead to an acceleration of respiration in those soils and lead to an increase in atmospheric carbon dioxide. So what do the scientists hope to discover through their data as they collect from the forest and from the tundra? So what are they really trying to get at here? Yeah.
Trying to see how all these different changes in Alaska play a larger role so that we can update models.
So we can update models. Again, this is complicated, right? We've got Alaska that's starting to dry out, and fires are becoming more frequent, which is burning off trees, which is converting them over to carbon dioxide. Then we have these deciduous species coming in, which is taking up carbon dioxide and reflecting light so that the planet's not heating up as much. It's effectively like ice, just bouncing that light right back into the sky. But then you've got the general warming taking place planet-wide, which is warming the soils, and it's like, well, what do? You've got these things that are sort of fighting back against climate change. You've got these things that are potentially amplifying climate change. You know, you just sort of shrug your shoulders and say, it's complicated, right? But what the scientists are trying to do is basically figure out exactly, how important is it in the global carbon budget that we have these deciduous species taking over, right, forests, and how important is that relative to soil thawing? Okay, so you've got the little greenhouse things going on. This is not a phased experiment. This is a greenhouse experiment. Where they're experimentally warming the tundra and seeing, like, okay, the temperature goes up 2 degrees, how much carbon's coming off. So they're basically trying to calibrate, if we're losing this much carbon per square meter, what does that mean over the grand scheme of things? So ultimately, they're just trying to measure carbon fluxes and how those carbon fluxes are going to change with climate change. About 10 minutes too ambitious before I have to get to the lecture today. We'll start looking at this idea of not detection, but climate attribution. So if detection is about finding something or finding a signal in climate data, attribution is fundamentally about determining what is causing the trend that we're detecting. So attribution is about identifying underlying causes associated with changes in climate. So it's fundamentally different than detection in that way. Detection is answering the question, is the climate changing? Attribution is what is causing the climate to change. So it's answering a different question. And as you go through the semi-text before Thursday, you're going to see you can sort of do a simple exercise and see what should the temperature of the Earth be. If you have a planet 93 million miles from the sun. What temperature should that be given that distance and the radiation traveling through space? And you would get you'd end up with sort of an answer like, well, the planet should be minus 20 Celsius. And you're like, that's not right. It's a lot warmer than minus 20 Celsius. So what we do is we're not just sort of random planet that's sort of stuck out there. Our planet has an atmosphere. So if we have a planet with an atmosphere which actually traps some of that, it starts to account for some of that. That's why we're not at minus 20, we're closer to plus 16 degrees Celsius. So we have solar output, we have other things that sort of affect what the temperature should be as well. Because we have ice at the North Pole and ice at the South Pole, when sunlight hits that, a little tiny bit of it gets absorbed, but most of it gets reflected back. So that energy is basically unavailable for the planet. Just bounces right back into space. So the question of whether or not the sun's energy is getting absorbed or getting reflected is going to play into this equation as well. And finally, because we have an atmosphere, there are the composition of the atmosphere is going to affect the temperature as well. We can have gases in the atmosphere that end up having a cooling effect, gases that have a warming effect. And we have a number of gases, including carbon dioxide, including methane, but also including water vapor, also including nitrous oxide, lactic gas, and also including refrigerant chemicals, most of which have been banned since the 1990s, chemicals that are CFCs, all of which have warming potential. They absorb the long-wave radiation that's sort of bouncing back off the surface of the Earth. So the question of what the temperature of the planet should be is sort of a first step towards solving this problem of attribution. We're going to pick up with attribution on Thursday. Be sure to read through sections 3, 4, 5.
Oh, God.